Think of a number between 1 and 100. If I guess 50, and you simply tell me higher or lower, I immediately know which half of the numbers to throw away. That basic process of elimination you used in childhood games relies on the exact same logic that powers modern computer science. But computers face a massive scale problem. They aren't guessing out of 100 options. They have to sift through billions of data points in a fraction of a second to find exactly what you're looking for. To do this without checking every single piece of data one by one, programmers use algorithmic patterns. An algorithmic pattern is a standardized logical shortcut that tells a computer how to navigate large data sets efficiently. High-level coding does not require complex, esoteric math. It relies on taking everyday human logic and scaling it up to bypass the constraints of time. Imagine looking at a massive, continuous sequence of data, and your job is to find a specific small grouping of items hidden somewhere inside it. Doing this efficiently means you absolutely cannot afford to start your search over from the beginning every time you check a new spot. Look at this diagram of a long row of shapes. Picture yourself looking through a small telescope at this row, but your telescope is so narrow it can only fit 3 items at a time. This is the setup for the sliding window pattern. The slow, inefficient way to search would be picking up the telescope, jumping ahead, setting it back down, and starting a completely new scan of the shapes you just landed on. The programming shortcut is much simpler. Instead of picking the telescope up, you just slide it exactly 1 spot to the right. By moving this way, you instantly drop the oldest piece of data on the far left, while your view simultaneously absorbs exactly 1 new piece of data on the far right. By maintaining that continuous window, the computer never has to read the same piece of data twice. An exhausting, repetitive search becomes a single, highly efficient sweep. Now let's look at a scenario where the data has already been neatly organized, like a line of people sorted sequentially from shortest to tallest. Your objective here is to find 2 specific individuals whose combined heights add up to an exact target number, say 200 centimeters. This chart shows our sorted data points. To find our match, we use the 2 pointers method, starting by placing markers on the absolute extremes of our dataset, the single shortest value on the far left and the single tallest on the far right. We add those 2 extreme values together. Let's say the shortest is 120 centimeters and the tallest is 100. That equals 220, which overshoots our target. Because the total is too large, there is no point checking that tallest person against anyone else in line. So the right pointer steps 1 position inward to swap the tallest value out for someone slightly shorter. The inverse rule also applies. If our combined sum had been too small, we would leave the right side alone and step the left pointer inward to find a heavier value. This mathematical relationship eliminates thousands of dead-end combinations. The target number itself dictates which end of the array moves next, pulling the search inward from the edges until the perfect match is found. Let's bring it back to that childhood guessing game to look at the most aggressive time-saving pattern in computer science. Imagine you are trying to find one specific target hidden somewhere inside a perfectly ordered sequence of 100 items. This sequence shows 100 numbered blocks. Instead of starting at the beginning, you guess the exact midpoint of the data, block number 50, to test if your hidden target is higher or lower. If 50 is too low, you don't just move to 51. The entire bottom half of the dataset is instantly eliminated from the search. You then rely on recursion to continue the search. Recursion is a programming technique where a process repeats its exact behavior on a smaller set of data. You jump to the midpoint of the remaining numbers, 75, and cut those remaining blocks in half again. Because you are constantly dividing the pool in half, there is a hard statistical guarantee. You can find any target out of 100 items in a maximum of 7 steps. When you escalate that scale, the math gets even more impressive. Finding one single item hidden inside 4 billion possibilities takes a maximum of only 32 guesses. Binary search alters the relationship between data size and search speed. By aggressively halving the dataset, it ensures that even as information grows, the time it takes to find a result barely changes. These conceptual metaphors make the logic easy to follow, but eventually you have to face the hard truth of implementing these patterns in actual programming languages. While some languages let you write loose scripts, applying these patterns in a language like Java comes with verbose, highly structured requirements. Java enforces strict typing. Strict typing is a programming rule where the data type of every variable must be explicitly declared and cannot change unexpectedly. This feature forces programmers to act carefully, designing sturdy blueprints for large-scale digital systems. Which brings us to the reality of learning data structures. Passively watching an explanation like this one only accounts for about 10% of the journey. The mandatory 90% happens when you are staring at a blank screen, actively struggling to make the code work. That period of friction is how your brain encodes the logic. The active wrestling with the syntax is what turns a difficult concept into a permanent part of your mental toolkit. So the next time you type a query into a search bar and get your answer in milliseconds, remember what's happening behind the screen. It is the direct result of these precise algorithmic tools, elegantly manipulating time and data.